Hello. Today we're going to work on a little problem of observing a coin underneath in a liquid pool, where the coin looks like it's half a meter, 0.5 meters from where it actually is. Let's calculate the depth of that. Perhaps we can look at the full question carefully. A person looks at the surface of the water with an angle of 30 degrees, and if I were that person, I would think that that was 30 degrees from the surface of the water and sees the coin 0.5 meters further than it really is. What is the depth of the pool? It can be interpreted as 30 degrees from the normal. I decided to work it the other way. If we look at the diagram, and I suggest that you make a diagram of this, we have the 30-degree angle here at which we're looking at the surface. But when we calculate refractive indexes, we need to use this angle up here, which is the angle between the normal and the line of sight. And the virtual image of the object is down here. The depth of the pool is labeled D. The index of refraction of the water is 1.33, and the index of refraction of the air is 1.00. Note that D is the cosine of this angle with this length, and D is the cosine of this angle with this length, L2. So let's go down and solve some of the numbers here. If we measure theta 0 is 30 degrees from the surface, then theta 1 has to be 60 degrees from the normal, and that's what we have to use. Theta 2 solved for that is 1 divided by 0.33 times 0.866. That's the cosine of theta 1, the sine of 60. The sine of 60 is 0.866, and the angle is 40.6 degrees. Based on the labels, as I pointed out before, what we were looking at, D is equal to L1 times cosine of theta 1, and D equals L2 cosine theta 2. Y, which is on the bottom, and 0.5 meters make up the sine of theta 1 when combined with L1, and Y combined with theta 2 is the sine of theta 2 combined with L2. And so these four relationships down here allow us to solve the problem. First, we solve for L1 and L2 in terms of D. L1 is equal to D over cosine of theta 1, and we have that. L2 is equal to D divided by cosine of theta 2, and we have that. So when we go to the second two equations, we substitute in for L1 and L2. Y is equal to L2 times sine of theta 2. Y is equal to D sine of theta 2 divided by cosine of theta 2, and that's equal to D times the tangent of theta 2. Y plus 0.5 is that the bottom distance. It consists of the shift in the thing plus the amount of baseline left over, and that's equal to L1 sine of theta 1. So Y here is equal to D sine of theta 1 over cosine of theta 1, minus 0.5. And that is equal to tangent of theta 1 times d minus 0.5. So if we eliminate the y's here, make this one equal the one above it, d tangent theta 2 is equal to d tangent theta 1 minus 0.5. Combining terms so that we end up with d on one side and the known things on the other side, d is equal to 0.5 divided by tangent of 60 and tangent minus tangent of 40.6. So the depth is equal to 0.43 meters. And that's what we wanted to solve. We can also solve for y, and it turns out that y is equal to about 0.36 meters. And the other thing you might want to do is to practice this. What if we interpret the problem as observing theta 1 equals 30 degrees from the normal instead of 60 degrees from the normal? You'll get different answers, but you work the problem exactly the same way.